the universe should not be younger than the oldest object that it contains. So that's the first check on this expanding universe idea. For a while it wasn't clear how well that check worked, but now it works. The age of the universe, projected by running the expansion backwards in time, is consistent with the oldest stars we can find. And the age of the universe is between 13, closer to 14 billion years, and actually now measured with quite high precision. So what about this expansion? How can we understand this expanding universe? Because it begs a question, of course, is this violating Copernicus? If everything is moving away from us, maybe we're special after all. Whew, I was really getting worried. You're all thinking you were going to have to buy this crap about us being sort of insignificant. No, we're the center. It's okay. It's cool. Well, no, we're not. We're not the center, because here we are on the red galaxy, and we look at galaxies, the blue and the red one, for example, the blue and the green, and we see them moving away from us, and the more distant one moves away faster, as Hubble's law said. But now translate your point of view to the blue galaxy, or the red one, and look around, and you see the same thing. Every galaxy sees the same thing. It's a democracy of viewpoint, and so no galaxy is the center. Every galaxy is the center, no galaxy is the center. And presumably, on this blue galaxy, not ours, there's a planet going around a star, and someone not called Hubble who named the law after them. And they're going to argue with Hubble when they eventually meet in whatever afterlife. No, that was my law. I saw that first. Well, did you account for look-back time when you say you saw it first? To describe the expanding universe, you have to use general relativity, which is definitely a whole different yarn than Newton's theory, which is linear space and time. General relativity accommodates the idea of curved space-time, in fact demands it, because matter curves space, as we saw in the little animation, on small scales, but on the global scale as well. Here's what the Hubble expansion looks like. So now we've got the idea of curved space in play. We can use the little model. There's no sound on this, is there? I'll better do it. Now that's tiring. So there are creatures in this curved two-dimensional universe, an analog, and they will see every other creature moving away from them. So there's a Hubble expansion. Now the key distinction between terrestrial physics, the physics we're familiar with, is that the Hubble expansion is a cosmological redshift because it's the lower situation. Space-time itself is expanding, and the galaxies are like witless, hapless victims, just being pulled apart by the expanding fabric of space. They are not moving through an external medium, as in the upper example. That's a Doppler shift. This is one of the fundamental conceptual changes of the idea that Hubble introduced, and Einstein really understood physically, that we're dealing with a situation where the universe itself is expanding. The galaxies are not moving like shrapnel through an external medium. There is no external medium. It's space-time itself expanding. And so we have a universe which may not have any boundary in space. And so to answer the Greek question, all the way through the ages, does the universe have an edge? It need not. It may only have an edge in time because of its finite age and the distance we can see with finite light speed in that age. We can't talk about a boundary in space, and we have not seen one. The other thing is that the universe has no center, logically, and it doesn't have to be expanding into anything. You just have to wrap your mind around that. And then the last weird component of the universe, which I'll say not much about, Mike will say more next week because we really don't know much about it at all, is dark energy. An entity, an agent of some kind physically, that is causing the universe to accelerate. So I'll briefly talk about it. It happened because we tried to trace the expansion rate back in time with more distant objects. When supernovae go off in a distant galaxy, these three galaxies are 3 to 5 billion light years away, and when a single star dies, it can rival the brightness of the galaxy, allowing us, because these are like standard light bulbs when they explode, to measure the distance to these galaxies. This allowed us to take the linear Hubble law, the smooth cosmic expansion, and project it to even earlier look-back times. What we predicted, what cosmology predicted, since the universe has mass, and mass will slow down the expansion, we predicted that as you go further back in time, you should see either constant or faster expansion. In other words, the universe should have decelerated since 5 or 6 or 7 billion years ago. What was observed with the red data points was that the universe was expanding slower in the past, which implies that it's accelerated since then, and that was a complete surprise, because we know of nothing that should make the universe accelerate. And so it leads to the idea of dark energy, which I will just introduce and leave Mike Turner to do the heavy lifting next week. And he's a theorist, and that's really one of his main subjects. And I will say very little about it for the simple reason that we don't know what it is. It's indicated by the observation I just showed. It's a repulsive force working in opposition to gravity. Its absolute level of strength is too weak to be understood by conventional physics, the physics of the textbooks you might have on your shelf, and that's about it. It doesn't seem to vary over time and space, but that's not been measured very well. And that's the third major ingredient of the universe. So we end up with a universe where definitely we're not the major part. In the pizza of the universe, we're a kind of paltry little slice that would barely keep a sparrow alive, and the dark energy and the dark matter, the dark forces that actually govern the cosmic expansion, acceleration, and deceleration are the overwhelming entities. So let's look back. Let's see how close to the Big Bang we can get. So here we are on the right-hand edge of the diagram in a big, empty, cold universe, looking back through time, through the aging of galaxies, towards the dawn of time, and a much smaller, denser, and hotter universe. We simulate this in computers. Now, in the computer, the expansion of the universe is done in the computer, and when I show a simulation, that expansion will be taken out. And so you can see that since this expanding hot gas is thinning out, gravity has to work against the expanding universe to congeal stars and galaxies. In a sense, it's lucky that it happened at all. Here's a simulation run from 500 million years after the Big Bang to the present day. It's 300 million light-year cube. And you see it goes from an initially smooth distribution to galaxies not randomly distributed, but strung along sheets and voids and filaments of a beautiful large-scale structure of galaxies, which is what we see in the real universe. The next one is the same but rotating, so you get a sense of the three-dimensional structures that form. And these structures are sculpted by the single force of gravity acting over 12 billion years. So, with our telescopes, here's how far back we can look. Our frontier instrument is still the Hubble Space Telescope until the James Webb Space Telescope, which the University of Arizona has an interest in both of these telescopes. And you can see that we're working our way back to a time that astronomers call the Dark Ages, before there were any stars or galaxies. If the universe started hot and smooth and with no structure, there must have been a time before there was light of any kind, and that's called the Dark Ages. Here's the deepest image of the sky ever made again. In this area, if on the sky would be the head of a pin, and there are about 4,000 galaxies if you cared to count them all. And just 2 weeks ago, the largest redshift or most distant galaxy was observed, this tiny little smudge zooming in 2 steps, which is seen as it was 13 billion years ago in a universe that's not much older than that. And that's pretty much the limit of our ground-based optical telescopes, or space-based. So we've pretty much seen to the edge of time, to the edge of the visible universe. Well, that's the story, but there's more. It gets weirder, because if you look back more than about 5 billion light years, any 2 objects in space were moving apart faster than the speed of light. Now, wait a minute, didn't Einstein say something about the speed of light being an absolute limit? That's his special theory of relativity. You know, he didn't get exhausted after that, though that's exhausting enough. He went on to the general theory, which describes the universe, and the general theory of relativity has no speed limit applied to the universe and the cosmic expansion. And if you trace the standard Big Bang model back, for most of the first half of the universe was expanding faster than light. which means that the light from those distant galaxies, as it was emitted, those galaxies were moving away from us faster than light. And it's only because the universe decelerated subsequently that light was able to eventually reach us. Now, a complication on that is dark energy, which is causing the universe to accelerate. And that means, even more weirdly, that some galaxies that we've been able to grasp with our telescopes will eventually have their light taken away from the telescopes, because once more they'll be ripped faster than the speed of light away from our view. It's pretty weird. And the implication of faster-than-light expansion of the universe, and this is profound and important, and it's a standard part of cosmology, not speculation, not the lunatic fringe of the subject, is that the physical universe, all that there is substantially, maybe vastly larger than the observable universe, what we can see to the limit of the Hubble telescope or any other. In other words, those 100,000 billion stars in 100 billion galaxies are not necessarily, and very likely not, all there is. That's just what we can see. So let's get back closer. Let's get real close to the Big Bang. And in fact, this is the best evidence that the Big Bang happened. So when that person sort of collars you in Walgreens or in a supermarket queue, and you happen to mention you heard talk in the Big Bang, and they say, "What's with that Big Bang thing? I don't believe that. That sounds crazy." You say, "No. Listen. Let me tell you about the microwave background." Because the microwave background, now that will convince anyone that the Big Bang happened. This is a picture of the microwave sky from a satellite, an exquisite image made just a year ago, but we've been trying to gather this data for decades. And it's a baby picture of the universe, looking far back before the oldest light in those galaxies. So we can do much better with this image, much closer to the Big Bang, than with visible telescopes. In fact, in the analogy, this is like a picture of you when you're a few hours old. That's how early it is in the history of the universe. It's a remarkable picture from just under 400,000 years after the Big Bang in a 14 billion-year-old universe. So you can think of the ratio. In that time, the universe has expanded by a factor of 1,000. It's got 1,000 times bigger and 1,000 times cooler. The physics is actually quite simple. And the way to understand why we can get an image like this is if you look at a cloud in the sky. The edge of a cloud is not a physical barrier. It's just the point in the cloud at which the density of water vapor diminishes to the point that light travels freely and reaches your eye, so you see an edge. Inside the cloud, there's still water vapor, but more, and the light bounces around. So it was in the universe. Before 400,000 years after the Big Bang, the universe was as dense as the atmosphere of a star, and light could not travel freely. After 400,000 years, the radiation travels freely, and we see an image of the early universe from that era. Since that era, those photons, that light, have been stretched by a factor of 1,000. So not only does the expanding universe carry galaxies away from each other, the waves of light that travel through expanding space are stretched by expanding space by the same factor. And so visible light, dim red light from the very early universe, is stretched by a factor of 1,000 into feeble microwaves. And that's what the satellite is seeing. Those microwaves are everywhere. There's 1 million or so in every breath you take right now. They fill this room. They're ambient radiation from the Big Bang in the universe. Because they're microwaves, they're not really noticeable. I've occasionally had people get worried. No, maybe in that same supermarket queue, someone gets worried about it. What, do you mean they're microwaves in space? I might get sterile, or something bad might happen. And if you do the calculation, I'll reassure everyone, and that the intrinsic radiation, the radioluminosity of the microwaves around you is 10 to the minus 5 watts of radio power. So it's like a 10 millionth of a light bulb worth of radio energy. It's not going to sterilize anyone. And it's not really very noticeable, why it was hard to find. And the Big Bang, because it's everywhere, is not a place. There is no place. It's every place and no place. It was a time, not a place. Very Zen-like, isn't it? And if you really want to see the Big Bang, you don't need a fancy radio telescope. Just take your TV and tune it between stations, and 1% of the speckles on the phosphor of your screen, if you have an old-style phosphor screen, are interactions of the phosphor with the microwave background radiation. And although your friends and kids and neighbors may think you're pretty weird staring at a screen doing that, I assure you that that station, the Big Bang station, is better than the crap on all the other channels. So we can't really get close to the Big Bang, but here's a cool thing that